In today's video, we're going to be testing out this 3000 watt continuous, 6000 watt surge, pure sine wave inverter to see how good it is. This one here is for a 12 volt DC input, which is ideal for recreational vehicles, large inboard boats, and trucks. For use with off-grid solar power systems, I recommend using a 24 volt or 48 volt input version. By using an inverter with a 24 to 48 volt input, along with an MPPT charge controller, that is definitely the way to go. By doing that, you're going to have lower losses in the wiring, and the wires that are used can be smaller in diameter due to lower current, which saves you money. This unit is also available in a 220 volt version, 50 or 60 Hertz. This unit was sent to me by the company, but that does not mean you'll be getting a biased review. If I see things I don't like, you're going to hear about them. And in case you're wondering, this is a highly affordable unit, and it has very high buyer satisfaction ratings. As usual, links have been placed in the video description area. When you purchase this unit, included with this is an instruction manual, 8 40 amp fuses, and you also get the cables to connect the inverter to the battery. Now these are 5 gauge wires, and a lot of these units they give you 2 wires instead of one larger one. Now I made a larger wire to test this unit, which you're going to see in a minute, but this is 5 gauge copper wire. I did open it up over here, scrape the wire to make sure it's not aluminum colored copper, and the terminals I scratched very deep, and they're also copper. In order to replace the fuses, you have to open up this cover, and you're going to see the inside of this unit in a little while. So let me place this off to the side. Right over here you have a larger display, and this display is going to show you the AC output voltage. Up here the smaller display is going to be the DC input voltage. In a little while I'll show you what each one of these LEDs mean. You have 2 grounded AC receptacles, and right over here you have this block. I can pop this off just to show you, and you can connect this directly to the AC wiring. Now the one thing I see that I do not like, and it's very minor, you can change it very easily, the yellow, because it makes you think this is a hot wire when it's actually the ground. So what they should have is a green cover going over this wire. You could disconnect this and slide some green over that. Very simple thing to do. And you would connect your ground over here, your hot, and then your neutral. Let me spin this around so we can take a look at the backside. Right over here, couple of air vents. There are openings in the sheet metal to allow you to mount this. On the rear side you can see the 2 cooling fans, and you're going to see how these are positioned in relation to the heat sinks when I open up the unit. Over here is the positive and negative input for the cables. You would double up the reds, put it here, double up the blacks, and put them on the negative side. Even though the surface underneath, and I could put it there, you might be able to see it. Let me open this. Appears to be brass, which is good. Let's get that out of there. I would have liked to have seen this bolt either copper or brass as well. And it's a minor change. You could run to a hardware store if you want to swap that out. But it would have been nice to see copper or brass. And here's a look at the opposite side. Another opening for the air. When the cooling fan is running, it's going to suck the air in through the opening on this side, the opposite side, and in the front, and it's going to discharge it out the back. According to the manufacturer, this unit has several different protections built into it. One is for low input DC voltage. One is for over voltage for the DC. You have overload protection. There's short circuit protection. So I should be able to short the neutral and the hot together, turn this on, and it should not destroy this unit. We're going to be testing that out. And I also want to see how much power is used by this unit when it's on standby. So I'm going to connect this up to the 12 volt battery. I bought a 12 volt battery just for this video. It is huge. You'll see it in a minute. It's a 4D battery made by Interstate, and it can easily power this unit for these tests. Okay, let me take this off the table. I'm going to place this on the ground, and I'm going to hook up my cables. And the battery cables I'll be using are the ones I made right here in a previous video. These are 4-aught stranded copper cables, and they can easily handle up to 300 amps of current. Okay, that's all set. Let me connect it to the battery now. We're all connected up to this 4D Deep Cycle Marine battery made by Interstate. I found this on OfferUp. It was a new battery. It was included with some heavy equipment, and they wanted to upgrade to a different battery. So I was able to get this one for only $140 without a battery exchange. And that's an incredible deal because these sell between $300 and $400. Now I want you to take a look right over here up close. What you're looking at is a 300 amp 32 volt fuse, and you definitely want to have a fuse between the battery and the inverter. The inverter is 3000 watts, so you want to use around a 300 amp fuse. You do not have to use a fuse. You can also use a circuit breaker like you see right here. This would be mounted on a board next to the battery or the wall, and you have your two connections. One would go from the battery with a cable to this post, and then you have the other post connecting to the inverter. In the event it trips, all you'd have to do is just push this back down. Now for the first test, what I'm going to do is turn on the power inverter. We're not going to connect anything to it. You'll see the display light up. It will be on standby, and what I want to do is measure how much current the unit uses when on standby. To do that, I'm going to be using this clamp meter that I showed you in another video. So let me turn this on first. And right down here you can see the AC voltage, and we're showing 12.7. It could be a little higher because there's only one decimal place. The blue LED means everything is okay and ready to go. Let me connect this up, take a look. Okay, let's put it right on this connection. And 635 milliamps. That's with nothing being plugged into the unit. The next thing I want to do is take a look at the output, measure the voltage using my digital multimeter, see how close it is to this reading, and then we're going to take a look to see if it's pure sine wave. Let's measure the receptacle, the output voltage, 121.7, we're at 122. Now remember, the red is the line, the black is the neutral, and I made this green because that's ground. Let's go here and there, same as this, and let's measure between line and ground, 61.8. If you go between the neutral and the ground, it's 59. All right, so basically this is center tapped, just like a center tap transformer on a utility pole. The neutral on the transformer is the center tap, so that's why we're getting 60 to here and 60 to there, and 120 across here. Now let's take a look at the output to see if it's pure sine wave. With the oscilloscope connected and the probe set to times 10, you can see the waveform right here very clearly. It is definitely a sine wave. 122 volts. The test I'm going to do now is going to be the low voltage DC and high voltage DC cutoff test. Now over here you can see we're showing 12.52 volts DC. The battery's disconnected, and you can see we're taking the power directly off this power supply unit, so it's 12.5, 12.5, and you can see we're coming in a little lower on the reading here. It says 12.3, so not really critical, but it would have been nice to see a little bit better accuracy on this reading. After all, the reading that I'm taking right here is right off the lugs on the back of the inverter. So this one here is high accuracy, and this one is off just a little bit. Remember, this could be 12.34, so it could be off about 0.15. I'm going to take the soldering iron and I'm going to plug it into this unit. Let's plug it in right here. Push this off to the side. You can see it over there. Something that would have been nice on this unit is some sort of an indication letting you know how much of the 3000 watts that you're using. But when you're only spending around $275 for a 3000 watt pure sine wave inverter, you can't expect too many features. Soldering iron is heated up, so let me start to lower this voltage a little at a time, and we're going to see when this triggers. Let's bring it down to there. So this is showing 11.5, this is showing 11.69. Let's bring it down to 11.75. Okay. So 11.43, 11.2 and 3 flashing. Let's bring it down to 11.5. This is now at 11, still supplying power. They say 10 volts is where this is going to trigger. 11. Let's bring this down to 11. 10.5. Output still 120. 10.6. Let's go to 85. Getting very close to the 10 volt range. A little bit more. 10.48. There you go. Low voltage alarm. Let me see if it actually turns off. Now the red light came on. So the low input voltage alarm, that worked fine. And then as soon as I lowered this a little bit more in voltage, it actually turned the unit off. You saw the red light come on. Now let's try it the opposite way. We're going to increase voltage higher and higher to make sure it turns off. 14.1. We're at 15. Voltage is staying about the same level. Let's go. We're at 14.9. 15 volts. Let's go a little higher. 15.1. The alarm should sound very shortly if it's going to be working properly. It's set around 15 volts. We're at 15.5. And there we go. Okay, so that works. It was a little higher than 15 volts. Now on to the next test. For the next test, we're going to be taking a look at the efficiency of this inverter. So I'm going to be plugging this in right here. It measures wattage. Plug it right in there. And I'm going to be using this hair dryer set to low. On low, it's going to use around 410 watts. I'm going to measure the voltage of the battery while this is running, and we're also going to take a current measurement on this cable. Let's get started. Now it's going to be very hard for you to see the reading on this one, so what I'm going to do is just plug it in to show you how many watts that it draws. Once that's done, we're going to concentrate on the reading of the digital multimeter for the battery and the amperage. And as you just saw, it draws 412 watts on low. Keep an eye over here while I'm measuring the current. 28.2 amps. And right here are the calculations to compare input power to output power. Now for the next test, I want to see how well this powers inductive loads such as a motor or a transformer. Now in a previous video when I tested the EcoFlow Delta, this saw you see right here, it would not power this saw. The saw is 15 amps and it has extremely high inrush current, but it was able to power a microwave oven. So if this inverter can handle this, you know it's going to handle a large microwave oven as well as your refrigerator. Let's give it a try. And here we go. No problem at all powering the saw. Now what I want to do is try and overload the unit. So now I'm going to use a toaster along with the hair dryer and then the circular saw. Let's give it a try. Here we go. Wow. Incredible. It did not get it to go into overload. We're going to use the toaster 1150. We're going to be using the hair dryer on high. That's 1450. So between the hair dryer and the oven, that's 2600 watts. And then we're going to add the circular saw, which is another 1400 watts. That's going to put us at 4000 watts. So let's give it a try. Hopefully it goes into overload. For those of you that would like to see the inside of this inverter, here you go. Right over here you can see the cooling fans and the very large extruded aluminum heat sinks that are positioned directly in front of the fans. So the air is going to be pulled through the ribbing in each one of these heat sinks to keep them cool. Over here are the MOSFETs rated for very high current. Over here are diodes, and over here you have more MOSFETs. Now if you take a look right here, this is the temperature sensor. When this heatsink gets hot enough, it turns on the cooling fan. If this heatsink gets too hot, the unit will shut down. We're going to test this in a minute. And a look at the opposite side. Over here are more of those high current MOSFETs. At this end where the AC receptacle is, you can see this very large inductor. There's another one over here. Then you have these large capacitors. There's another capacitor over there that's gray, and at the very end, you may not be able to see it, there's a blue relay. These are used to filter the AC output. Over here you can see all the connections that are made. You can see the 4 transformers, and on each one of these lugs there's 4 wires. So we have 4 reds, they're doubled up on each side, so there's 2 here and 2 there, and they appear to be 8-gauge wire. Each one of the red wires connects to a location on the board next to each one of the transformers, and there are 2 40-amp fuses in parallel. There's a female blade connector that each one of the fuses plugs into, so all you have to do is take a needle nose, pull them out, and then install a new one when they blow. What I'd like to do now is just scrape into the surface of this bar to see if it is bronze or brass all the way through. Take the blade on the screwdriver and just very gently scratch deep, and that is definitely the same color all the way through. So it's not steel, it's either brass or bronze. For the last 2 tests, we're going to be checking the temperature sensor. My power supply unit is set at 12.7 volts. This is already powered on. You can see that right over here on the left. I'm going to take this mini heat gun and I'm going to heat up that sensor just like the MOSFETs and diodes would be heating up that heatsink. I'm going to heat it, and at a certain point the fan should turn on. So let's give it a try. And there you go. Fan is now running. And it's not hot enough that I can't hold my finger on it. It feels like it's around 120, and it's probably going to turn off in 1 minute because this aluminum heatsink is still pretty cold. And as expected, it just turned off. So what I want to do now is I'm going to leave the camera on the front side showing the 122 volts, 12.6 for volts it's showing on the front panel. We're going to keep an eye on that, and I'm going to continue to heat this past the point when the fan comes on, because I want to make sure that if this gets too hot, that the unit will shut down. So let's do it again. Fan is on. Alright, it just turned everything off, and there's actually a little red light flashing. You can see it on my hand, and it just automatically reset. So that's working. So in the event this does get too hot, it will shut down the inverter. It'll cool just enough to power back up and then have the fan come on. We're now going to test protection for AC output short circuit. You can see this extension cord. I have the prong shorted using a copper strip. I'm going to turn this on, and then we're going to plug it in and see if this turns off. According to the manufacturer, this inverter here should not blow up performing this test. I moved to the outdoors just to be safe. Okay, let's give it a try and hopefully it works. Turn this on first. Leave this right over here in front so you can see it. I'm going to plug this in. Hopefully this does not blow up, but we're going to find out. This should go off right here. Let's see if it recovers. Maybe I got to turn it off to reset it. And let's see. Okay, so this is not coming back on. The unit didn't blow up, but let's take a look at the fuses inside. Maybe the way it's designed, you won't damage the unit, but you may blow the fuses. So let's take a look. Okay, what I did is I checked each one of the fuses. There's 8. None of them are blown. That is not a good thing. All the MOSFETs and diodes on both sides, no problem at all. I don't see anything burned here. But when I go to turn it on and reset it, you can see right over here it is not lighting up to show the output voltage. I even tested the output to see if there's any voltage present, and there is none. Boy, am I glad I performed this test last, because I would have never been able to complete the other test. This unit is now dead. So I do not recommend short-circuiting the output of this unit. You will definitely destroy it. It's a shame because it performed very well, but they should not be telling people that you can short-circuit the output if you're going to end up damaging the unit. And guys, that is it. I hope you enjoyed this review. If you did, be sure to rate thumbs up, share, and check out my extensive video playlist for many other videos of interest to you. Thank you very much for watching.